Episode 10, final episode. Everything you learned about RAG has one blind spot: relationships between things, who worked with whom, what caused what, which companies share the same investors. GraphRAG solves this by turning your documents into a knowledge graph. This is how the best production RAG systems are built. Let's finish strong. Welcome to the final episode of the advanced course. Here is the question that breaks standard RAG. What companies have received investment from funds that are also backing our competitors? Your documents have this information scattered across dozens of board announcements, press releases, and SEC filings. Each chunk contains some of the facts, but no single chunk contains the full picture. Standard vector search finds chunks that are semantically similar to your query. It returns the 10 most relevant passages, but it cannot connect the dots across them. It cannot follow the chain. Fund A invested in company B. Company B competes with company C. Fund A also invested in companies D, E, F. That traversal requires a graph. This is the fundamental limitation of flat vector databases. They are excellent at recall, finding relevant information. They are poor at reasoning over relationships, connecting information across documents. GraphRAG is the solution. The core idea is, before you store your documents, extract the entities and relationships from them. Build a knowledge graph. When a user asks a question, query the graph to retrieve relevant subgraphs. Connected networks of entities alongside relevant text chunks. Send both to the LLM. Microsoft's research team published the definitive GraphRAG paper in 2024 and open sourced the implementation. Their system constructs communities of related entities using graph clustering algorithms, generates community summaries, and provides two query modes: local search, find specific entities and their neighborhoods, and global search, answer questions that require understanding the whole data set. Let me walk you through the architecture. Step 1 is entity and relationship extraction. You pass each text chunk to an LLM with a prompt that instructs it to extract entities and relationships. The LLM outputs structured triples: subject entity, relationship type, object entity, and a short description of the relationship. An example triple from a tech news article might be: OpenAI acquired Rockset. OpenAI acquired vector database, startup Rockset in 2024. You collect thousands of these triples from your full document set. Deduplicate entities by name. Merge relationships that describe the same connection from different documents. Step 2 is graph construction. Load all your triples into a graph structure. In Python, NetworkX handles this with a single call: gadd edge with subject, object, and relationship metadata. For production scale, Neo4j is the right choice. A purpose-built graph database with Cypher query language and native graph algorithms. Step 3 is community detection. Real-world knowledge graphs have clusters, dense subgraphs of highly connected entities. These clusters represent topics. In a financial data set, a cluster of related companies with shared investors. In a medical data set, a cluster of symptoms, conditions, and treatments. In a tech data set, a cluster of libraries, frameworks, and their authors. The Leiden algorithm is state-of-the-art for community detection. Run it on your graph, and it assigns each entity to one or more communities. Then use the LLM to generate a summary for each community, a paragraph describing what this cluster of entities represents and why they are connected. These community summaries become a high-level index of your knowledge. Step 4 is hybrid retrieval. When a query arrives, you run 3 retrieval passes in parallel. First, vector search on your original text chunks. Second, Entity search. Extract entities from the query and retrieve their graph neighborhoods using cipher traversal. Third, community search. Find which communities are most relevant to the query using embedding similarity on community summaries. Merge the results. Deduplicate. Rank by a combination of semantic similarity and graph centrality. Entities with more connections to other retrieved entities are more likely to be central to the answer. Here is the full GraphRAG pipeline using Microsoft's GraphRAG library and a NetworkX local implementation for when you do not have a Neo4j instance. First, install the dependencies. Microsoft's GraphRAG package installs with pip. For the local graph approach, NetworkX and Community are the key packages. Microsoft's GraphRAG configuration is a YAML file. You specify your input directory, your LLM for entity extraction, your embedding model, and your output directory. You set entity extraction to identify person, organization, geo, and event entity types. You set the claim extraction to capture relationships between them. You define your community detection algorithm as Leiden. Run the indexing pipeline with GraphRAG index. It reads your documents, calls the LLM for entity and relationship extraction, builds the graph, runs community detection, and generates community summaries. This takes time for 1,000 documents. Expect 15 to 30 minutes. You run this once and update incrementally when new documents arrive. For queries, use GraphRAG query in local mode for entity-specific questions, or global mode for questions that require dataset-wide understanding. Local mode does entity graph traversal. Global mode aggregates across community summaries. For the DIY approach without the Microsoft library, which gives you full control, here is the pipeline. Define an extraction prompt that takes a text chunk and returns JSON with an entities array and a relationships array. Each entity has a name, type, and description. Each relationship has source, target, relation, and description. Call this extraction on each chunk using the OpenAI API in batch mode. Collect all your chunks, process them with Asyncio by gather for parallel extraction, pass the JSON responses, handle passing errors with a retry, build the NetworkX graph from your extracted triples, detect communities with the Python Louvain library. For each community, collect all entity descriptions and relationship descriptions within it. Call the LLM with a summarization prompt to generate a community summary paragraph. At query time, use the entity extraction function on the user's query to find mentioned entities. For each mentioned entity, retrieve its neighbors in the graph up to 2 hops deep. Convert the subgraph to a text representation. A list of entity A relates to entity B via relationship type strings. Combine this subgraph text with the top 5 vector search results. Send both to the LLM. Your context for the LLM now looks like relevant text chunks from the documents, plus a structured relationship map showing how the entities in those chunks connect to other entities. The LLM can use the relationship map to answer multi-hop questions, track chains of relationships, and identify indirect connections that no single chunk would reveal. Benchmark this against your previous RAG setup on multi-hop questions. Questions like which experts have co-authored papers with researchers who also worked at company X, or what sequence of events led to outcome Y will show the biggest improvement. Simple factual recall questions will show similar performance. GraphRAG does not hurt single hop retrieval. It adds multi-hop capability on top. Your final challenge, take a data set you care about, your company's documentation, a collection of articles in your domain, any set of text, and build a GraphRAG index over it. Use Microsoft's GraphRAG library for the indexing. Ask it 3 questions that require connecting information across multiple documents. Compare the answers to what standard RAG returns on the same questions. You are not going to go back to flat vectors for complex knowledge bases after you see this work. You have now completed the Advanced AI Engineering course. You built production RAG that rivals enterprise systems. You fine-tuned your own models. You built stateful multi-agent graphs. You ship AI with proper observability and evals. You can handle voice, vision, and multimodal inputs. You built AI products people actually pay for. You optimize prompts automatically with DSP. And you built knowledge graphs that understand relationships, not just similarity. That is not beginner work. That is not even intermediate work. That is the skill set of the engineers who build the AI systems other people use. Go build something real with it. 10 episodes from advanced RAG to knowledge graphs to automatic prompt optimization. You are not an AI user anymore. You are an AI engineer. What you build next is on you. I cannot wait to see it.